This unit focuses on estimates and sample sizes, and in this lesson we will learn about estimating a population proportion. To review, in chapters 2 and 3 we used descriptive statistics when we summarized data using tools like graphs and statistics such as the mean and standard deviation. Then in chapter 6 we learned a little bit about critical values. We're going to focus more on that in this lesson. This chapter presents the beginning of inferential statistics. The two major activities of inferential statistics are 1. To use sample data to estimate values of a population parameter, and 2. To test hypotheses or claims made about population parameters. We introduce methods for estimating values of these important population parameters, whether they be proportions, means, and standard deviations or variances. We also will learn methods for determining sample sizes necessary to estimate those parameters. In this section, we present methods for using a sample proportion to estimate the value of a population proportion. The sample proportion is the best point estimate of the population proportion. We can use a sample proportion to construct a confidence interval to estimate what the true value of a population proportion is. And we also will need to know how to interpret those kinds of confidence intervals. We also should know how to find the sample size necessary to estimate a population proportion. A point estimate is a single value or point used to approximate a population parameter. The sample proportion p hat is the best point estimate of the population proportion p. The Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. The best point estimate of p, the population proportion, is the sample proportion p hat, which is told to us to be 85%. So we represent p hat as a decimal 0.85. A confidence interval or interval estimate is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI. A confidence level is the probability 1 minus alpha, often expressed as the equivalent percentage value, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called the degree of confidence or confidence coefficient. The most common confidence level choices are 90%, 95%, or 99%. For 90%, alpha is 0.10 or 10%. For 95%, alpha is 0.05, and for 99%, alpha is 0.01. We must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval 0.828 is less than p is less than 0.872. We are 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion p. This statement means that if we were to select many different sample sizes of size 1007 and construct the corresponding confidence intervals, 95% of them would actually contain the value of the population proportion p. In this correct interpretation, the level of 95% refers to the success rate of the process being used to estimate the proportion. A standard z-score can be used to distinguish between sample statistics that are likely to occur and those that are unlikely to occur. Such a z-score is called a critical value. Critical values are based on the following observations. 1. Under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. And 2, a z-score associated with a sample proportion has a probability of alpha divided by 2 of falling in the right tail. 3, the z-score separating the right tail region is commonly denoted by z sub alpha over 2 and is referred to as a critical value because it is on the borderline separating z-scores from sample proportions that are likely to occur from those that are unlikely to occur. A critical value is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely to occur. The number z sub alpha over 2 is a critical value that is a z-score. It has the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. For our first example, we're going to find the critical value z sub alpha over 2 corresponding to a 95% confidence level. Do not look up 0.95 in the body of table A2 since we're trying to find a critical value. First, let's take a look at what the picture of a 95% confidence level looks like on a standard normal distribution curve. So we set up the standard normal distribution bell-shaped curve, and we're going to have 2 marks on either side of the curve that's going to align with this critical value that we're searching for. Now the confidence level 95% means we have a 95% area in the middle of the curve that's bounded by those 2 marks. So our leftover area is 1 minus 0.95, or it's 100% take away 95%. So we have 5% area left over together in the 2 tails of the curve. If we divide that by 2, alpha over 2 is 0.025, or 2.5% in each separate tail. Now we know what to look up in our table. So what we're going to do is we can look up the total area to the left of this boundary. So if I take 1 minus 0.025, that gives me 0.975. So if I look up 0.975 in the body of table A2, I will see that that number appears there exactly, and it corresponds to the z value of 1.96. Because of symmetry, then we know the other mark is negative 1.96. Another way to find this is to look up just 0.025 in the body of table A2, which is going to give us the negative z-score value. So if I look up 0.025, that will give me negative 1.96, and then because of symmetry, we know the other z-score would be the positive 1.96. Let's practice finding the critical value that corresponds to another confidence level. Let's use 92%. So what would the area left over in the tail of each curve be? So alpha is 100% minus 92%, or 8%. The decimal equivalent is 0.08. So the area located in each tail is alpha divided by 2. 0.08 divided by 2 is 0.04, or 4%. So we're going to scan the body of the table, and I'm going to look up 0.04, which is going to give me the negative z-score value. Now the closest value in the body of table A2 to 0.04 exactly is going to be 0.0401. The z-score that is aligned with that is negative 1.75. So the critical value would be z sub alpha over 2 is plus or minus 1.75. Here are some common critical values that we'll be using for our formulas in this lesson. So the confidence level of 90% has an alpha of 0.10, and so the critical value for a 90% confidence level will always be 1.645. For the confidence level of 95%, the critical value will always be 1.96. And for a confidence level of 99%, the critical value will always be 2.575. So these answers are achieved by the process we learned on the previous two examples, and you can always use that process if you have a confidence level that is not a common one. Let's take a look at the table A2 to see where these common critical values are located. So if we go to table A2, if you look at the bottom of the positive z-scores, you will see common critical values located down here on the bottom right. So these are confidence levels 0.90, 0.95, 0.99 with the common critical value for those. So let's go back to our examples in the lesson. When data from a simple random sample are used to estimate a population proportion P, the margin of error, denoted by capital E, is the maximum likely difference with a probability 1 minus alpha between the observed proportion P hat and the true value of the population proportion P. The margin of error E is also called the maximum error of the estimate, and it can be found by multiplying the critical value and the standard deviation of the sample proportions. So the margin of error is E equals z sub alpha over 2 times the square root of P hat Q hat over N. Here's some notation we'll be using for our formulas. So lowercase p is population proportion. P hat is the sample proportion. N is the number of sample values, or the total in our survey. E is the margin of error. And z sub alpha over 2 is the z-score separating an area of alpha over 2 in the right tail of the standard normal distribution. Z sub alpha over 2 is a critical value, and it's associated with a given confidence level. So, when we set up a confidence interval for estimating the population proportion P, the sample should be a simple random sample. Also, the conditions for the binomial distribution need to be satisfied. There should be a fixed number of trials, the trials need to be independent, and there have to be two categories of outcomes. Also, the probabilities should remain constant for each trial. The third requirement is that there should be at least 5 successes and 5 failures. So this is the setup for a confidence interval estimate. It is P hat minus E is less than P hat plus E, where the margin of error E is estimated by z sub a over 2 times the square root of P hat Q hat divided by N. So when we set up this confidence interval, we'll need to make sure that we always put a P in the middle, because this is the true value of the population proportion that we're trying to estimate. And we get a left side number and a right side number. This is the range of values that P could be estimated to be. You also could generalize this formula as P hat plus or minus margin of error, and you can write it as an interval. The round-off rule for confidence interval estimates of P tells us to round the confidence interval limits for P to 3 significant digits. Here's our procedure. First, verify that the required assumptions are satisfied. 2. Refer to table A2 and find the common critical value that corresponds to the confidence level in the problem. 3. Evaluate the margin of error using the formula. 4. Using the value of the calculated margin of error E and the value of the sample proportion P hat, find the values of P hat minus E and P hat plus E. Then set up your interval. Always round the resulting confidence interval limits to 3 significant digits. Here's our first example. In the chapter problem, we noted that a Pew Research Center poll of 1,007 randomly selected adults showed that 85% of respondents know what Twitter is. The sample results are n equals 1007 and p hat equals 0.70. So we want to first find the margin of error E that corresponds to a 95% confidence level. Then we want to find the 95% confidence interval estimate of the population proportion P. Then we have some follow-up questions. So when the problem says do a confidence interval estimate, then we're doing the P hat minus E is less than P is less than P hat plus E, where E is critical value Z times the square root of P hat Q hat over N. So in this problem, we need to search for the critical value Z. So that comes from the confidence level of 95%, and we can get that from table A2. P hat comes from the sample. So if we look back at the problem, it tells us that the sample results are n equals 1007 and p hat is 0.70. So this right here is my p hat. So q hat is going to be 1 minus 0.70. It's the complement of p hat. So q hat would be 0.30. That's enough information to find the confidence interval. So the formula is set up where we have the common critical value Z that goes with the confidence level of 95% is 1.96. We multiply that by the square root of 0.85 times 0.15. So I guess on this problem they're going back to 85% and not using the 0.70. So let's disregard that there. They're using 85% from the sample and plugging that into the formula. So if we use p hat as 0.85, then q hat is going to be 0.15. And we divide that by 1007. So let's look at how to enter this in the calculator in one step. So the first thing we want to do is kind of move from left to right. Most calculators are set up like that. So we do the 1.96 and then we get the square root. So the square root is located above the x squared button. And to access that we have to do second x squared, and so it should paste that to your screen. Usually it comes up with a parentheses opening. And then we're going to do the numerator. So we type 0.85 times, not parentheses, 0.15, and then go directly into the division, divided by 1007. Okay, and then you can close the parentheses and press equals, and you should get this value here for the margin of error. Now notice I'm not rounding it to the nearest tenth or hundredth. I'm being generous with the decimals there, and that's because this is not my final answer. I still have another step to use. So the interval is p hat minus E is less than P is less than P hat plus E. So I just need to take my margin of error and I need to subtract it from my P hat, which was my sample proportion, and add it to my sample proportion. So I get 0.85 minus margin of error is 0.828, round to 3 decimal places when we estimate the P. And then 0.85 plus the margin of error gives me 0.872. So based on the confidence interval obtained in Part B, it does appear that more than 75% of adults know what Twitter is. So that 75% was what we're comparing this to, and we can see that we are pretty confident here that the true value for the population parameter is going to be from 82.8% to 87.2%. So it's definitely more than 75%. So because the limits of 0.828 and 0.872 are likely to contain the true population proportion, it appears that the population proportion is a value greater than 0.75. Here is one statement that summarizes the results. We could say that 85% of U.S. adults know what Twitter is. That percentage is based on the Pew Research Center poll of 1,007 randomly selected adults. In theory, in 95% of such polls, so this comes from the confidence level, the percentage should differ by no more than 2.2 percentage points. So this right here is the margin of error, and we're rounding it off for our report. in either direction from the percentage that would be found by interviewing all adults in the United States. So this is just one way to interpret the interval that we had. So when analyzing polls, always keep these under consideration. 1, the sample should be a simple random sample, and it also should not be an inappropriate sample like a voluntary response. 2, the confidence level should be provided. It is often 95%, but media reports often neglect to identify it. 3, the sample size should be provided. Also, it is usually provided by the media, but not always. 4, except for relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample, but the size of the whole population is usually not a factor. Never follow the common misconception that poll results are unreliable if the sample size is a small percentage of the population size. The population size is usually not a factor in determining the reliability of a poll. So now what we want to do is look at other ways to represent and find the point estimate and margin of error. So let's say that we have a confidence interval set up, and we're told that the range of values for p could be estimated between 0.875 and 0.880. Well, from any confidence interval, you will be able to backtrack and find what the original p hat was, or point estimate was, and the margin of error. So to do that, when you have an interval, is you can just add the upper limit and the lower limit together and divide it by 2 to get p hat. To find the margin of error, one way to do it is to subtract the limits and divide by 2. So let's express the confidence interval 0.456 is less than p is less than 0.496 in the form of p hat plus or minus e. So from this interval, we need to find p hat and margin of error. P hat is upper confidence level limit plus lower confidence level limit divided by 2. So 0.456 plus 0.496 divided by 2 is 0.476. If you're entering this in the calculator in one step, you'll need to do parentheses around the sum of the numerator. So p hat is 0.476. That is the point estimate. That means that in their sample, 47.6% was what they had. Okay, so now let's find the margin of error E. E is the distance between the point estimate and the ends of the interval. So one way to do that is to just subtract the p hat that we found, which was 0.476, from either number that was in the interval. So if we take 0.496 minus 0.476, or if we take 0.476 minus the other number, 0.456, we get the same value, 0.02. Or you could take 0.496 minus 0.456 and divide by 2 to get 0.02. So the margin of error is 0.02. So we can represent the confidence interval in the form of p hat plus or minus margin of error, and substituting our answers we get 0.476 plus or minus 0.02. So now let's look at another example. If our n sample size is 1200 and x is 200, that means that in our sample we had 200 people out of 1200 people that were successful with whatever this study was. And we have a 98% confidence level. So what we want to do here is find the margin of error E and set up a confidence interval. So the formula is p hat plus or minus. Now notice I took out the E and I just have the formula here. So what we're accustomed to seeing up until this point is it's p hat minus E is less than p hat plus E, where the margin of error is this formula here. So let's substitute into that formula to find margin of error. Now first I'm going to find p hat. Now p hat is another percentage in the problem that's not the confidence level. In this problem, we don't have it. So then what we do is we search for two numbers that we can divide. And my two numbers are the 200 and 1200. So 200 divided by 1200 is 0.17. Now, when you are estimating p hat by dividing like this, you do have to be careful about how you round your answer. Now this right here, I rounded it to 0.17. Now to get a more accurate answer, especially on your test and your homework questions, it's better to round p hat to 4 or 5 places because it's going to be used inside of the square root again. So don't round to the nearest tenth or hundredth, go out to about 3, 4, 5 places. So q hat is 1 minus p hat. So if I'm using 0.17, then my q hat would be 0.83. So now the common critical value for 98%, well, it's not really a common one, so we need to backtrack and figure this out. So we're going to really do 100% minus 98% is 2%. So in the tails of our normal distribution, I have 98% in the middle and I have 2% left over in both of these extreme regions here. So if I half that, I get 1% or 0.01 area. So in this little left tail, I need to find what is the critical value that has 0.01 area in it. So I'm going to look in the body of table A2 on the negative z-scores and find the closest area to 0.01. As you scan through, you'll find that the closest is 0.0099. So the critical value that aligns with that would be negative 2.33, and because of symmetry, we also have the positive. Now for the formula, we don't substitute plus and minus into it, we just use the positive critical value. Okay, so my margin of error is going to be 2.33 times the square root of 0.17 times 0.83 divided by 1200. So the margin of error is 0.025. So to do my interval then, I'm going to take p hat minus the margin of error and p hat plus the margin of error. So that gives me 0.17 minus 0.025 is 0.145. And 0.17 plus 0.025 is 0.195. So my interval is 0.145 is less than p is less than 0.195. Okay, so now that we've learned how to set up a confidence interval estimate that contains the true value of the population proportion, now we want to know how to collect sample data in order to estimate that population proportion. So we need to know how many do we need to obtain for our survey or for our research. So if we've done a sample and we have an estimate for p, this is the formula that we would use to find n. So n is z sub alpha over 2 squared, so it's the critical value squared, multiplied by p hat multiplied by q hat, and then we divide that answer by the square of the margin of the error. Now let's say we don't have any idea what to use as an estimate for p. So in that case we use the formula n equals critical value squared times 0.25 divided by margin of error squared. So the difference here is that we are assuming p hat and q hat are 50%. And if you multiply 0.5 times 0.5, you get 0.25, and so that's why we have that value there. If the computed sample size n is not a whole number, which it usually won't work out to be one, we always want to round the value of n up to the next larger whole number. Now the reason that we do that is because we're dealing with discrete data. So we're trying to figure out how many people or how many objects do we need to obtain for our research, so we always round up to the nearest whole person. Many companies are interested in knowing the percentage of adults who buy clothing online. So how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So we're studying two formulas in this lesson. One, setting up a confidence interval estimate, which is the p hat minus margin of error is less than p hat plus margin of error. The second formula we're learning is the n formula. Now, the way you know which one to set up is the N formula will always be asking how many. So if we look at this, it says how many adults must be surveyed. So we're using the N formula here. Okay, now they're giving us some information in Part A. Use a recent result from the Census Bureau. So this recent result is 66% of adults buy clothing online. So that's another percentage there, and that's actually from a sample or from research that was done. That is a p-hat value. That's an estimate for the population proportion. Now, in Part B, we're going to assume that we don't have that prior information. Okay, so we're going to use that p-hat is 0.66 in Part A, and q-hat is 1 minus p-hat, or 0.34. Also, alpha is 0.05. Remember, that was a 95% confidence level, and so the critical value that's always associated with that is 1.96. Now, in this problem, they said the margin of error, we want it to be within 3 percentage points. So if the margin of error is given to you where it uses the phrase percentage points, they're giving you E as a percent, and you need to convert it to the decimal equivalent. So my margin of error is 0.03. So the formula for N is critical value squared times p-hat times q-hat divided by margin of error squared. So we have 1.96 squared. So to access that, you just hit the x squared button on your calculator. We're multiplying that by 0.66 times 0.34 and then divided by 0.03 squared. Now this answer is not a discrete answer. It's 957.839, and so we don't use normal rounding rules here. What you always do, no matter what this decimal number is, always round up. So maybe it would be like 957.3. So sometimes we would say, well, that would be 957 because the 3 isn't going to make the 7 go up to an 8. Well, actually, that's incorrect. We need to survey at least 958, and that's because this is saying we need to survey 957 people and some more. And because you can't survey part of a person, you have to go to the next person. So we always round up when we do a sample size. So in Part B, we're told to use the same information except assume that we don't have a prior study to estimate p-hat. So in this case, we use 0.25 for the product of p-hat and q-hat because we're just assuming that they're both 50%. So 1.96 squared times 0.25 divided by 0.03 squared is 1067.111. So again, doesn't matter what the decimal is, you don't use normal rounding rules. You always round up. So we need to survey at least 1,068 adults. Use this given data to find the minimum sample size required to estimate a population proportion or percentage. So in this problem, it doesn't say how many, but it says find the sample size. So that's an N formula. We're told the margin of error is 0.05. Okay, so this is not 5 percentage points. So don't convert this. E is going to be just 0.05. Now our confidence level is 99%. That always gives us our critical value Z. And p-hat and q-hat are unknown. So this is the N formula that I would use in this situation. If p-hat and q-hat are unknown, then I use the product 0.25. The critical value that is associated with a 99% confidence level is 2.575. So I have 2.575 squared times 0.25 divided by 0.05 squared. Instead of typing this all in the calculator in one step, you could estimate separately, and you get 663.06. Always round up, so we need 664 in our sample. So now our margin of error is 5 percentage points and our confidence level is 90%. From a prior study, p-hat is estimated by the decimal equivalent of 65%. We want to do a sample size, so we're doing an N formula. Now, since they say we have a prior study and we have a percent, we're going to use that for the p-hat. Also, the critical value that is associated with 90% is 1.645, so we're going to square that. We multiply that by 0.65 p-hat times q-hat, which is going to be 1 minus 0.65 or 0.35. Divide that by the margin of error squared. So the margin of error was 5 percentage points. So if you see percentage, then it was given as a percent, and you've got to change it to the decimal equivalent, which is 0.05. So N is 246.25, so always round up, 247. The Genetics and IVF Institute conducted a clinical trial of the Y-sort method designed to increase the probability of conceiving a boy. As this book was being written, 51 babies were born to parents using the Y-sort method, and 39 of them were boys. Use the sample data to construct a 99% confidence interval estimate of the percentage of boys born to parents using the Y-sort method. Based on the result, does the Y-sort method appear to be effective? Why or why not? Okay, so first, p-hat is estimated by x divided by n. So they did not give us another percentage in the problem, but they did give us two numbers to divide. So let's backtrack and look at what those two numbers were. So we have 51 total babies, and it says 39 were boys. So I'm going to do 39 divided by 51 to estimate the percent of boy babies that were born in this study. 51 is going to be n. And then the 99%, that's our confidence interval, and that's going to be my critical value z. So we have a choice here on the formulas in this particular lesson. We either are going to do the p-hat minus margin of error is less than p p-hat plus margin of error. That's a confidence interval estimate. Or we're going to do the N formula, which is a sample size formula. Now this says construct a confidence interval estimate. So I'm doing this formula here where I need to know the margin of error. So when I divide 39 by 51, I get 0.76. So now let's go ahead and set up the margin of error. So it's critical value times the square root of p-hat q-hat over n. So I have 2.575. That's the critical value for my 99% confidence level. Multiply that by the square root of 0.76 times 0.24 divided by 51. So if p-hat is 0.76, 1 minus 0.76 gives me q-hat, 0.24. So the margin of error is approximately 0.154. So now I want to find my interval by taking the p-hat minus the margin of error and p-hat plus the margin of error. So I have p-hat, which is 0.76. I'm going to subtract 0.154, and that's going to give me 0.606. 0.76 plus 0.154 will give me 0.914. So we're 99% confident that the interval from 0.606 to 0.914 actually contains the true value of p. So we can assume that this method is effective because of its high probability of producing a baby boy. The music industry must adjust to the growing practice of consumers downloading songs instead of buying CDs. It therefore becomes important to estimate the proportion of songs that are currently downloaded. How many randomly selected song purchases must be surveyed to determine the percentage that were obtained by downloading? Assume that we want to be 95% confident that the sample percentage is within 1 percentage point of the true population percentage of songs that are downloaded. So notice that this question says how many. So that's an N formula. The N formula requires us to either know the p-hat or it's unknown. So search for another percentage in the problem or find two numbers to divide. Now in this setup, the only percentage is the one that goes with the confidence level, and I don't have a prior study that gives me two numbers that I can divide to find the percent. So p hat and q hat are unknown, and so that's where we use the 0.25 in the end formula. Also, it says we want to have the sample percentage be within 1 percentage point. So that's my margin of error. I want it to be within 1%. So we need to convert the margin of error to the decimal equivalent of 0.01. So let's go ahead and set up the end formula. So I have critical value squared times 0.25 divided by margin of error squared, which is 1.96 squared times 0.25 divided by 0.01 squared. This end formula works out exactly to 9,604 that would be needed in our sample.